Hello students, this is our second lecture on fundamentals of design. So that is stresses and strain. We will see what is stress and strain. Then we'll also see stress strain diagram for ductile and brittle materials, and we will discuss about types of stresses. So students, what is stress? When any material or a component is subjected to external forces, external force, at that time that component will develop some internal resistive force, and that internal resistive force per unit cross-sectional area is known as stress. Stress is denoted by sigma, S, F. Mathematically, stress is equal to load upon area. Load is in Newton, area is in mm square. So unit of stress is Newton per mm square. It can be in Newton per meter square, megapascal, etc. So we will see correlation between various units. 1 Pascal is 1 Newton per meter square. 1 kilopascal is 1 into 10 raised to 3 Newton per meter square. If we convert that Newton per meter square into Newton per millimeter square, it comes 1 into 10 raised to minus 3 Newton per mm square. 1 megapascal is 1 Newton per meter square. 1 into 10 raised to 6 Newton per meter square. If we convert it into Newton per millimeter square, 10 raised to 6 upon 10 raised to 6. So it comes 1 Newton per mm square. 1 gigapascal is 10 raised to 9 Newton per meter square. 10 raised to 9 upon 10 raised to 6. So it comes 10 raised to 3 Newton per mm square, which is also known as kilonewton per mm square. Next, we will see what is strain. So when any component is subjected to external load, there will be deformation in the component. Dimensions will change. So this change in dimension to the original dimension when subjected to external load is known as strain. Strain can be linear or it can be lateral. When the force is applied in x direction, then the strain produced in x direction will be linear, and strains in y and z direction will be lateral. If change in length is positive, that means linear strain is positive, then lateral strain will be negative. As we can see, it is the ratio of two dimensions, so strain is unitless. Now we will discuss about stress strain diagram. So here we can see this is a stress strain diagram for ductile material. Strain is on x-axis and stress is on y-axis. Material we have tested, specimen we have tested on a universal testing machine, and whatever values of stress and strain we have observed that are plotted, and it is shown like this way. You can see that beyond point O, if tensile load will increase up to point A, stress is directly proportional to strain. So material will follow Hooke's law, and this point is known as proportionality limit. Beyond point A, if we further increase tensile load, then stress and strain both will increase, and material will behave in such a way that After removal of the external load, material will regain its deformation, or you can say size and shape back. So point B is elastic limit and this range is elastic region. In elastic region, material will regain its original size and shape. Beyond point B, if we further increase the tensile load, you can see that stress increment is very small as compared to strain. So in a component, creep formation will start. There will be slow deformation up to point C. And here this point is known as upper yield point. Beyond point C, if we further increase the tensile load, then stress value decreases but strain value increases. So you can see that curve falls down up to point D, and point D is known as lower yield point. Beyond point D, if we further increase the tensile load, stress and strain both will appreciably increase and there will be deformation of a component, and up to point E, material will be able to withstand maximum value of the stress without failure, and that point is known as ultimate stress. Beyond point E, if further tensile load is increased, then stress value decreases but strain is increased. And the point at point F means neck formation. Beyond point E, neck formation will start, necking will start, and from the necking somewhere, point F, there is a fracture of the component, and that is why this point is known as breaking stress. Students, in the plastic region, material will be permanently deformed. So that permanent deformation of the material is known as permanent set. In ductile material, there is 30% maximum permanent set is possible. Here I have shown various salient important points which we have studied. Now this is a stress strain diagram for brittle material. Brittle means cast iron. Okay. So here when stress is plotted versus a strain, we can see that up to point B, when load is applied, stress is directly proportional to strain. So this point P is known as proportionality limit. Beyond point B, P, you can see further increment of the tensile load, material will behave in an elastic way up to point Y. So point Y is known as elastic limit. Further increment of any tensile load, there will be deformation only slight and without much appreciable deformation, without increment of the strain, material will be subjected to fracture, and that point is known as ultimate stress or breaking stress. So here in brittle material, ultimate stress and breaking stress are the same. Next, we have in our syllabus various types of stresses. Which all types of stresses we are going to study? That is tensile stress. Here you can see pictorial view. Then we are going to study compressive stress. We can see from this diagram. Bending stress, you can see the beam is subjected to bending. So bending we will be studying. we will see transverse shear stress. Upper diagram is showing single transverse shear stress and the lower one is showing double transverse shear stress. Then we will see component subjected to twist, so it will be a torsional shear stress. Then we will see punching shear stress. Punching shear stress means a punch will fall on the component and it will create a hole, and that is known as the punching shear. Then we will see crushing stress. Crushing stress, this is an example of a key of the crushing stress. And last we are going to study, that is bearing stress or bearing pressure. So students, I hope you have enjoyed learning this, and here we are going to discuss all these types of stresses in detail in the next lecture. Thank you.